welcome to baby step 2. Congratulations for making it this far. Now let's start on homogeneous equations with constant coefficients. Now we're starting second order differential equations, as you can notice from the second derivative symbol on y. We often have problems, differential equations looking like this, where we have in standard form, obviously, y double prime plus ay prime plus by equals to 0. Now that we have a second order differential equation looking like this, in order to solve these equations, we start by assigning these y double primes as r squared, and this y prime will be r and y will be a constant. So anytime you want to solve homogeneous equations, this is important. These are homogeneous equations. You can notice it from this being 0, causing it to be homogeneous. Okay, so that y double prime would be equal to r squared, y prime equals to r, and y equals to constant. So keep that in mind and build this form: r squared equals to ar plus b from here. And then what you want to do is solve for r. Once you solve for r, you have three cases. One, either r1 equals to r2, and these must be real numbers. So when r1 is equal to r2 and they're real numbers, our solution becomes c1e to the r1t plus c2t e to the r2t, where y is a function of t. This is important. If it's a function of x, replaces t with x, basically. The second case is r1 is not equal to r2. This is distinct roots. Distinct. Okay? And this is also equal roots. So distinct roots, when you have distinct roots like this and they're real numbers, the solution becomes c1e to the r1t plus c2e to the r2t. Notice how we had a t e to the r2t? We drop that t over here, and our solution becomes this formula right here. And finally, our third case is when we have complex numbers as r, right? When we solve a quadratic equation, sometimes we get complex roots, and when we have complex roots, our solution sets become e to the at, where a is the real part of either of the solutions, and c1 cosine of bt, where b is the unreal part of the solutions, and plus c2 bt, c2 sine bt. So many of you may ask, do we not use the r2, or do we not use the negative b? That's actually a very logical question, and the answer is it doesn't matter. You can use r1 or r2. Even if you put negative b inside this, you will ultimately get the negative inside the cosine will generate a cosine, positive cosine, because cosine is an even function. And when you put a negative b here, you're going to get a negative c2 sine bt. However, negative c2 is also another constant, so you would do a plus c2 sine bt. So it doesn't matter which one you use. I think it's best to use the positive ones. Just use the a and the b in front of the I, and build this formula. These formulas, they kind of do require some memorization if you want to solve these problems really quickly. So I would advise you to just memorize these formulas. Also, the more you solve practice problems on this concept, it will help a lot, and eventually you'll be really comfortable with these solution types. So now let's work on this very nice example: y double prime plus 2y prime plus y equals to 0. So how do we solve this differential equation? Well, this is a homogeneous second order differential equation, and we have constant coefficients, right? So we can use this method we just covered, and now we're going to write this as r squared plus 2r plus 1 equals to 0. Okay, and now we need to solve this quadratic formula, which is actually really easy from algebra. You can just write this as r1 plus r plus 1 squared, and this will give you this quadratic formula equals to 0. And now we know that r1 equals to r2 equals to -1. So we have equal real roots. So what was the formula for equal real? Let's just note that real quick. Equal. The formula is e to the r, or c1 e to the r1t plus c2t e to the r2t, considering y is a function of t. And now that the solution becomes really easy, y equals to c1 e to the, in the first times you can just copy it from the cases just for practice, and then eventually I hope you all can know which one to use. C1 e to the -t, because r1 is -1, and r2 is also same as r1, so you can just trade, it's just going to be the same, and plus c2 times t, c2t e to the -t is our solution for this problem. Now let's work on this very nice example. Y double prime plus 5y prime plus 4 equals to 0. Well, since this is a homogeneous differential equation with constant coefficients, we can use this method again. R squared plus 5r plus 4 equals to 0. And this is a very nice quadratic because this can be dissolved as r4 and 1, and we can do this, and eventually you would get r plus 4 multiplied with r plus 1 to generate r squared plus 5r plus 4 from algebra. And then these roots become really easy to see. The first root, r1, will be -1, and the second root, r2, will be -4. So now that we have distinct real roots, because r1 is not equal to r2, we should now use the formula for distinct roots. And that was c1 e to the r1t plus c2 e to the r2t. Okay? This is equal to the solution of the differential equation. So now let's do it. The solution of our differential equation will be c1 e to the r1, which is -1, so -t, plus c2 e to the r2t, which is -4t, equals to, and this is equal to y. So here's our solution for this differential equation. Now let's work on this very nice exam problem. We are given y double prime plus 2y prime plus 2y equals to 0. And since this is a homogeneous equation with constant coefficients, we are free to use this method, r squared plus 2r plus 2 equals to 0. Well, this is really hard to factor out, so what we can think about is maybe using the quadratic formula, and delta is equal to b squared minus 4ac, and the solution sets r1 comma r2 is -1 plus or minus square root of delta over 2a, where our equation is in the format ar squared plus br plus c. So using this quadratic formula, we can see that delta is going to be equal to 4 minus 4 times 2 times 1, which is -4. So delta equals to -4, and square root of delta is going to be square root of -4, which is actually just 2i from algebra. So the solution sets will become -b, which is -2, plus or minus 2i over 2 times a, which is 1, so we're going to have 2, equals r1 comma r2. Okay, so now that we have this, we can just simplify it. r1 is going to be equal to r1 equals to -1 plus I, r2 equals to -1 minus I. So I'm just gonna go with the positive version because it's much more easier. So our solution sets for complex solutions is e to the at times c1 cosine of bt plus c2 sine of bt, where a is the real part and b is the non-real part of the solution. So our solution for this differential equation will become y equals to e to the real part, negative t, negative 1 times t, negative 1 times t, or negative t, multiplied with c1 cosine of t, because the constant in front of I is just going to be 1, so you're going to have cosine of t plus c2 sine of t for this differential equation.